My name is Zhou. I'm an assistant professor at the University of Iowa. So this work is done with my student, Zhou, and my colleagues, Tianbao, James, and Ricardo. So the title is Predicting Traffic Accident Through Heterogeneous Urban Data, a case study. So in this work, actually, we are trying to address an important, interesting, but challenging problem. That is predicting traffic accidents. So this is our first attempt to address the challenges in this work. We collected some data and we proposed some ideas to improve the result accuracy. So as you can tell, this is a challenging problem. And we hope that this work can bring some interesting ideas and we can discuss what can be done to solve this problem better. So a little bit about the motivation. Motor vehicle crashes, that's a more formal name of the traffic accidents we talk about. This means the traffic accident usually involves at least a motor vehicle. Okay, vehicle collide with each other or hit or crash with a human or pedestrian. So this is a big public safety issue apparently. In 2013, over 1 million people were killed globally by traffic accidents. And in our state, Iowa, we have over 570,000 traffic accidents or motor vehicle crashes between 2006 and 2016. That's on average just 157 per day. And because Iowa is actually not a very highly populated state, we don't have a large population. So this is actually very small compared to other states like New York and California. But this certainly caused life loss and property loss. And other issues like traffic delays, congestions. So it's very important for people to figure out how to prevent or reduce the risk of traffic accidents and motor vehicle crashes. So two quick examples. This is the map of Iowa. So this is our capital city, Des Moines. So this was actually a big traffic accident caused by a snowstorm because we snow a lot in winter. It's very hard to drive on the highways. And the second is here. This place is called Williamsburg along I-80 interstate. So this is a big traffic accident, and also in 2015. So a big truck hit other cars and actually exploded. So there's a long queue of traffic congestion. The reason why I'm showing these two is because I was actually at the scene for both of these traffic accidents. So this one I was driving back to Iowa City along I-80, and for this one I was somewhere here. I had to stay on the interstate for 2 hours after this accident. So there has been a lot of research, actually. This is not a new problem. Many people have tried to analyze traffic accidents to learn insights and knowledge. For example, what has caused accidents? What are the most important factors that led to the accidents and how to reduce the risks? So if we look at related work, there has been a lot of papers talking about either using supervised methods or unsupervised methods to analyze traffic. For example, some people have formulated this problem as a classification problem. Okay, they want to predict if there will be an accident on certain road segments or on certain routes or in a certain region. So method-wise, people have used decision tree, random forest, neural networks, SVM, all kinds of tools. So this is classification. Other people formulate it as a regression problem or just simply perform a correlation analysis. So these people want to predict the total number of traffic accidents along certain roads or in certain regions. So they use different kinds of regression models, logistic regression, negative binomial regression, Poisson regression, or you can also use neural network to give a numerical prediction. So this is the second category. And the third category is unsupervised analysis. So most of them do hotspot analysis, okay? Finding regions or routes with higher density of traffic accidents. So then people can try to avoid these regions when they drive the cars. But if you look at all these literature, there's one issue we identified. So most of these work are done by domain experts or from domain perspective, like civil engineering, public health, public safety, or injury prevention. So there has not been much work done by data scientists or data miners to address this from data mining perspective. So this is an observation, actually. It's not limitation because these scientists also do very good work. But there's some issues with this research. First of all, many of these papers just use limited data, okay, in terms of volume and features, because collecting data to perform this analysis is not very easy. And second, most of these papers just simply apply some existing methods or tools like decision tree, random forest, or neural networks. So because of this simple application, they may not address technical challenges very well, which I'll discuss in the next slide. So as a result, there's some issues such as overfitting and other problems. So generally, the prediction result is not very good. It's around 60% or 70% accuracy, although they are using different data, but there's still a lot of room to improve this work. So our problem is a binary classification problem. This is how we formulated this work. So basically, for each road segment in a big road network, and for each 1 hour time slot, so this is a combination, we want to predict, or we want to classify this road and hour combination into one of these two classes, with accident or without accident. Okay, so this is a binary classification problem. And as you can see, this is a very challenging problem. So first of all, there is a class imbalance problem, because accidents are actually rare events, right? You don't see traffic accidents every hour, every day. So usually within a few days or even a week, you don't see any traffic accidents along any road. So if you compare these two classes, this positive class or with accident is definitely a very, very rare class. So this class imbalance issue is a big problem. And second is spatial heterogeneity. So consider a global prediction model. Okay, let's say we learn a global model from all the road segments, from all the data. So if you want to use this single model to do the prediction, it may not give you very accurate results in some regions, because if you look at the causes of accidents on rural street or urban streets with very low speed limits, and on rural highways with very high volume but fast traffic, the causes could be very different. So that means model from place to place will change. And if you build a global model, you will have low accuracy. So that's what we call spatial heterogeneity. And also data sparsity. So then people say, okay, if there's spatial heterogeneity, can we build one model for each road segment? Unfortunately, you cannot do that because, again, accidents are rare. And if you do that, you will have data sparsity issues. So for many road segments, you don't have any traffic accidents in the past 10 years. And so that's very hard for you to predict what's going on in the future, what's going to happen in the future. So as I said, this is a first attempt in our project to address these issues. So we can see that there's some improvement in the results. So first, we collect many heterogeneous data sets and process them to generate our training and testing samples. We propose an informative sampling strategy as opposed to random sampling to kindly address the class imbalance problem. We also incorporate spatial graph features to address the spatial heterogeneity issues. And then we do a lot of experiments to see if these ideas make sense and if they really improve the performance. So let me talk a little bit about what data we use, data sources. So the first data is, of course, motor vehicle crashes. So actually, we have the data from the Iowa DOT. They share the detailed motor vehicle crash information from 2002 to 2013. But we can only use data from 2006 because other features, they don't cover the years before 2006. So actually, there are a lot of information given for each crash. Vehicle, driver, the gender, age, everything about the drivers. But we can use only time and location. This is because we only have these detailed information for accident drivers and cars. We don't have this information for non-accident drivers, right? We cannot pull over a car on the street and see the driver's age and gender and make a record. So we only have record for accidents. So that means a lot of information cannot be used in the current problem formulation. So this is a visualization of the crashes in the state of the Iowa. You can see most of the accidents are concentrated around the large cities and along major roads. And the second data we have is high resolution rainfall data. This is from National Weather Service, actually. By using radar, you can actually give a very accurate estimation of the amount of rain in each hour. So the unit is millimeter. The reason why we call it high resolution is that actually we partition the region into very small tiles. If you zoom in, you can see these are small squares, 4 kilometers by 4 kilometers. So we have 8,026 such tiles, and where in each tile we have hourly precipitation measures. And weather information. So other information include temperature, wind speed, humidity. So these information are measured by some stations along the highway network. So this is from the roadway weather information system in Iowa. We have 86 stations to measure these informations for over 10 years. This is also hourly data. And we need to have the road network, of course. So we have different versions of the road networks, and along the road networks, we know the number of lanes, traffic speed, and also the average annual daily traffic, AADT. And we also have the breakdown of this measure for different types of vehicles, like trucks and buses. And finally, we also incorporate some demographic data. So we find these census tracts in Iowa. So each of them is a census tract. We get the population and the area so that we can calculate the population density of these regions. So we incorporate these 5 data sets. So the underlying message is that we believe that traffic accidents are related to weather, location, and population density. So population density sort of reflects the level of development of the regions. So we believe these factors may contribute to accidents. So data pre-processing. So first we need to combine the road networks and partition the road networks. So finally we get over 12,000 road segments. Because on each road, if there are 3 different speed limits, then we need to partition the road into 3 small segments. So we have a very detailed road network. And there's some missing values from the stations. So we did some interpolation by using the weighted average of the 3 nearby stations. And actually, we did a quick test to see the error. Actually, for all these attributes, our error is very low, which means our method is working. And then finally, we match these weather data onto each road segment. So for the stations, we do this Voronoi diagram. And for the rainfall data, it's just the tiles. So we average all the tiles or partitions that overlap with each road segment. We use the average measure as the measure for that road segment. And finally, we match the points, the traffic accident locations, onto the network. So it's a point-to-network matching. So this is a summary of the data. So after the processing, we have, for each road segment in each hour, there are 40 features. So 7 of them are road features, like the length or curve degree, speed limit. Temporal features. So temporal features is independent of the location, right? Daytime, holiday. Weather information. So this weather information is related to both time and location. So we have temperature, humidity, wind speed, so on and so forth. Finally, we have some social features, population density, and the traffic. So we consider traffic as a social feature because it's related to human activities. So in total, we have 40 features. And after the map matching, if we find at least 1 accident along a road segment during a specific hour, then we consider this road segment and our pair as a positive sample. So we make the label 1, that means accident. So this is a summary. You can see there's some distributions of accidents. So morning rush hour here and evening rush hour here, they are peaks for accidents. So all these curves, all these plots shows the positive class, okay, the feature distribution for accidents. Okay, so then we can perform our prediction. We can build our model. So a few steps. First, routine step, we need to do some feature engineering to normalize numerical features and binaries categorical features. That's routine process. Then we need to do negative sampling. Because in the previous step, after we match the accident, everything we get are positive class, right? So each road segment with accident, that's the positive class. So technically, any road segment without any accident could be considered as a negative sample. But there are so many such samples. We cannot use all of them. Otherwise, we have a big problem of imbalanced classes. So we need to address that. And then we address the spatial heterogeneity problem. So instead of using random sampling, here we use informative sampling. So the goal is to actually sample more near the decision boundaries so that we can have a better performance. So here we pick 3 features: hour, day, and road. So we start to believe that these attributes have the most important influence on the accident, because hour and day, they can determine the weather information, and road can determine the location. So many other features are controlled by these 3 features. So we change only one of them and keep the other 2 as the same as before. And for any active accident or positive class, if we change the hour and get another sample without an accident, then we use that sample as a negative sample. Same thing, we change only the day. For example, 1 p.m. today, on this road there's an accident. Then we change it to 1 p.m. tomorrow on this road segment. If there's no accident on that day, then we use that as a negative sample. So we do this and get 3 times the negative samples compared to the positive samples. And we use that to build our model. And the next approach we use is to use spatial graph features to address spatial heterogeneity. So technically, you can use different methods. For example, model ensembles. You can build different models. You can partition the data into different regions. Okay, you can partition the road network into different regions, and for each region, you can build a model, right? But as I mentioned, then you will have data sparsity issue. Some partitions will have so few data samples, then you have very low accuracy for those partitions. So what we do is we perform a simple spectral analysis of the road network. So it's like a soft clustering. So we do a spatial clustering without the last step, which is the k-means clustering. So first of all, we construct the adjacency matrix of the road network. Okay, so let's say we have 4 different road segments. If they are intersecting, they share an intersection, then we consider they're connected. Then we can construct this adjacency matrix for the entire underlying road network. Then we perform the spectral analysis. So we calculate the Laplacian matrix of this, this underlying spatial graph. And we get the first k eigenvectors associated with this k smallest eigenvalues. So actually, this is a standard spectral clustering process. The goal is to partition the entire road network into k components such that each component are strongly connected. Okay, so but we do not. So the key here is that we do not use k-means in the last step to really partition the graph into k partitions. Rather than that, we actually use these eigenvectors as new features. So for example, we have a parameter k, so we have k different clusters. So each of these columns, from x11 to xk1, that's k features for the first road segment. Okay, and the second column could be the k features for the second road segment. So by doing this, we have k additional features to represent the topological relationship among different road segments. And we incorporate those features into this classification model. So this shows you the spectral clustering result using k equals 10, 20, 30, and 40. Okay, actually in our method, we don't classify them, so the features are actually numerical. But you can see when we increase the number of clusters, some large cities like Des Moines and Iowa City, they can be clustered into a single group. Okay, so then we can run our experiments. We test decision tree, linear SVM, random forest, and deep neural network, which is a single feed-forward neural network with 3 hidden layers. We also add a job-out layer to avoid overfitting. So we test these common models, which one works best, and we also want to test if our proposed ideas can improve the accuracy. So since we have 7 years of data, we use each year as training and the next year as testing. So basically, we learn model from year 1, do the prediction from year 2, and we average the accuracy or the measures from all of these years. So first group of result, informative sampling versus random sampling. So the result is measured using the AUC curve, AUC score, area under curve. So looks like from this should be random forest. So decision tree and random forest, we can see that our informative sampling can increase the accuracy. However, for neural networks, it seems that the difference is not so much. No matter which sampling strategy you use, the performance are very similar. So that's the number one comparison. In number two comparison, we measure AUC, precision recall, F1 score, and accuracy of all the models by increasing the number of the clusters, or K. So you can see that neural network with K equal to 30 has the best performance. And if you compare with when K equals 0, all of the measures are significantly improved. So on the right side, you can see these ROC curves, and RF and neural network, the spatial features, spatial graph features improve these results quite significantly. But linear SVM is not giving any good result because the problem is nonlinear. So SVM is not preferred in this context. And also we test what is the impact of increasing the data volume. So we train the data with year 1 plus year 2, year 1 plus year 2 plus year 3, so on and so forth, and predict the following year. So you can see as we increase the data volume, all the models have some improvement, especially the neural network is consistently the best one. But at the end, there's some drop because there's some overfitting since the model changed over years. So that is the result we present. And the conclusion is that, first of all, this problem is not a linear separable problem. So linear model like linear SVM does not work very well. And incorporating spatial graph features could significantly improve the results, which means that we address the spatial heterogeneity properly. Informative sampling improves the results for some models, but not for neural network. And increasing data volume can also increase the result. So in the future, we would like to incorporate more interesting features like geosocial features and explore other types of neural networks to solve this problem. All right? And I would like to acknowledge the founding agencies and collaborators. Thank you very much.